Another example of Rolle's theorem. We have another polynomial function, and this time we have our function g of x is equal to x cubed plus 8x squared plus 21x plus 18. We're over the interval -3 to -2. And we want to first of all determine if Rolle's theorem applies. And then secondly, if it does apply, then what are the values that satisfy Rolle's theorem? All right, so now the good news is that this is a polynomial function. And because it's a polynomial, automatically numbers 1 and 2 are satisfied. All right. But the third condition, okay, for Rolle's theorem says that g at A is going to be equal to g at B. So how do we know that that's true? So let's go over here and let's see if that works. All right. So now going back to our function, just really quickly, our function is x cubed, 8x squared, 21x, 18. And so we're going to substitute 3 back in there. Okay, so we're going to say, or -3, excuse me. So -3 cubed plus 8x squared. And in this case, x is -3. Notice I'm using parentheses for everything. Plus, I think it was 21x. So that's 21 times -3. And then I think the last one was 18. It is. All right, and that's going to give us negative, or I'm sorry, maybe I made an error here. Let's see. That gives us 0. All right, so let me go back. Okay. So let's substitute -2 back in. All right, and hopefully that gives us 0. So I'm just going to change all the 3's to 2's. So bear with me. All right. And it does give us 0. All right, so that's good news, because if they didn't give us the same thing, then we would be in trouble. All right, so g at 3 is 0, or -3, and g at 2 is 0. And because they both are equal to one another, right? Doesn't have to be 0, but g at 3 equals g at -2. So all 3 of the conditions satisfy. So right away we know that there has to be some value. Right, now we're going to find the derivative. Right, so remember our original function, x cubed, 8x squared, 21x, 18. Now g prime at x, our derivative, 3x squared, 16x plus 21, right? And we're going to set that equal to 0. There's 2 ways that we can try to solve this. First of all, we could try to factor it. If it is factorable. If it's not factorable, then we're going to use the quadratic formula. All right, so let's use the quadratic formula first, all right, because I think a lot of our students would probably go through, they probably use the quadratic formula because they look at this and they just don't want to tool around with the right numbers, right? So remember our quadratic formula, minus b plus or minus the square root b squared minus 4ac divided by 2a. Right? And in this case, a is 3, b is 16, c is 21. So that's going to be the opposite of 16 plus or minus the square root of b squared, which is going to be 16 squared, minus 4 times 3 times 21, all divided by 2 times 3. All right, now we're probably going to go into our calculator, and we're just going to compute this guy right here. All right, so x is going to be -16 plus or minus. We know the denominator is 6 because 2 times 3 is 6. So in our calculator, we're going to have 16 squared minus 4 times 3, not -3, but 3 times 21. All right, and that's going to be 4. All right, which we know is 2. So it's going to be -16 plus or minus 2 over 6. And now we're going to add and we are going to subtract. All right, so Now we know that negative 16 plus 2 is negative 14 over 6, or that's negative 7/3. That's one of our solutions. And then the other one, we're going to subtract, so that's negative 18 over 6, or negative 3. All right. Now we know negative 7/3. If I was to approximate that, that's negative 2.333, etc. And that's good because remember our original interval was negative 3 to negative 2. So this number clearly falls inside of that interval. All right, that's good. That's what we want. We don't want negative 3 because remember negative 3 is actually the value in the interval. All right, so for us, the only value by using the quadratic formula is going to be negative 7/3. All right, now for those of you that like to factor, okay, let me just show you that you can factor this and actually get the answer a lot quicker if you're okay with factoring. All right, so I'm going to go back here. Let's erase all this good stuff with the quadratic formula. All right, not that it's wrong. Okay, oh, I didn't delete it. I meant to. I just hit the wrong button. I think I hit home instead. All right, so we're going to delete that. All right. And if we were to factor this, for those of you that probably factored it, well, we know that 3x squared is 3x and x. And we know that 21 is found by 7 times 3. And we can't put 3 here because then we'd actually have another factor of 3 in there. All right, so that's a pretty cool trick that maybe some of you guys could use, is that more than likely when you're factoring, if you put something that's divisible by another coefficient, that's probably not right. All right, and how do we check it? Remember, the trick to checking these is you multiply the inside, you multiply the outside, and 9 and 7 gives us 16x if we add those together, which is the middle term. All right, so those are this, I'm sorry, excuse me, this is the correct factorization. And then we just set both these to 0, for 3x plus 7 equals 0, and then x plus 3 equals 0. Now this one we know right away is x equal negative 3, which we already knew from before. All right, so notice right here we get x equal negative 3. We're going to subtract 7, and then we're going to divide by 3, and that's negative 7/3, which we already knew from the quadratic formula. But if we can factor, we could do this problem a heck of a lot quicker than if we went through and tried to use the quadratic formula. And also, quadratic formula may lead to a lot of errors in computation. All right, so hopefully this illustrates not just going through and using Rolle's theorem, but making sure you check your answer, and then also utilizing some of the techniques to solve these equations. An extension of Rolle's theorem is going to be something called the mean value theorem, which we're going to take a look at in the next video.